So good day, my name is Carl Bergmann. I'm a Senior Technical Specialist in the Minerals Processing Division at Mintek. The purpose of today's talk in the context of fines processing is to remind everyone of how important incorporating mineralogy can be. I'm going to talk about three things. It'll be quite a short presentation. The first topic is what type of mineralogy are we going to discuss? What kind of type of mineralogy is useful? Secondly, I want to go into the topic of liberation. What is liberation? How do you measure it? In a bit more detail. And then finally, a couple of examples of how this approach can be useful. So the type of mineralogy we're going to talk about is called process mineralogy. Mineralogy as a whole is a very large field, from crystallography all the way up to geology. So we really want to look at that part of mineralogy that studies minerals in relationship to commercial processes. In process mineralogy, what would you want to do? First of all, you need to get a representative sample. That is a whole topic on its own. Generally, you're looking at a few grams of material under a microscope or under some piece of equipment, and it's very important that that little sample is representative of the feed or the sample or the process that you're looking at. Then step one is to identify all the minerals that are there. First of all, just what are they? Then, how much is there of each mineral? What's often forgotten is to say each mineral is not textbook in its quality. So often you've got to do a probe of the mineral that you're looking at and see how clean is the mineral itself. Has it got inclusions? Have there been changes to its crystal structure or its composition? If there has been changes like that, it can greatly affect the kind of products that you can make through your process and the kind of qualities that you can. In mineralogy, there are many other things you can measure as well. Shape and texture, states of liberation, which minerals are touching which other minerals. So, step one would really be to characterize the sample. Your fines processing step, particularly, it will be your feed. What's in the feed? And on this particular table, you can see a number of characterizing methods. It's not all of them, but it's the most common. The first four people are very used to. For instance, characterize the sample by a sieve analysis or by a laser scattering. And then you get the size distribution of your feed. Very often people will then assay each size fraction, and there's many different methods of chemical analysis to get the assay of each size fraction. If you're interested in density separation or gravity separation, you may use heavy liquids and fractionate your sample into many density classes, and in that way characterize how well it can be treated by gravity. If you're looking at milling processes, you may characterize your sample by all sorts of comminution indices, bond work and crushability, etc. Now the 7 topics that follow are really an example of carrying on the characterization process using mineralogy. Using mineralogy is a very powerful tool to assist in understanding what's possible with your sample. Sometimes it's very difficult to understand and quantify what's in front of you. For instance, if you look at some of these photographs here, where you've got needles and very strange shapes, how are you going to give that a size? What size is a needle or a fiber? Looking at mineralogy, you need to understand things like how rough or smooth a particle can be. Is it porous or not? Because that will affect its density. Are the mineral surfaces clean, or are there very thin coatings that may influence a flotation process? So mineralogy can go into a lot of detail if necessary. And often it's not necessary to go into this level of detail. Here's an example of liberated minerals of the same size but of different shapes. So a simple SEM picture can give you this type of information where you've got a distribution of particle shapes that may go into a separator. And even though they're the same mineral and they're the same size, because of their shape, they may separate quite differently. If we go more into the meat of the presentation, it's really about liberation. And what do we mean when we say liberation? So to understand liberation, you really need to understand the difference between grains and particles. And when you talk about liberation, it's always with respect to a grain and how it is associated with a particle. So in this figure, we can see three little diagrams. Now the mineralogist will normally cut through in a polished section through your sample and can have a look and see inside the samples. Here's an example where you have a grain and a particle as the same thing. It's completely liberated. This example is a particle consisting of two grains. This is a particle consisting of multiple grains. And of course you can bear in mind that particles can come in different sizes and shapes, and the grains can come in different sizes and shapes. So when you talk about liberation, you need to decide which grain, which mineral am I going to refer to when I want to see and quantify how liberated it is. You can't ask the question, how liberated is a particle? You have to say, how liberated is the grain inside the particle? So how would you quantify this? It's normally done in two different ways. The first method is called by grade, and the second method is called by free surface. If you look at these three particles, they are all made of two grains, grain A and grain B, or mineral A and mineral B. From a mass or a grade perspective, all three of these particles have the same state of liberation. They all have 25% mineral B, 75% mineral A. And that type of liberation is enough if you're doing a gravity process. Those three particles have the same size, they'll have the same composition, and they'll have the same density. So they should go to the same place in the gravity process. However, if you're looking at a flotation process, you need to change the definition of what type of liberation you mean. And that's when we talk about liberation from the point of view of free surface. So now if you look at those same three particles and you say, I want to float mineral B, then you'd say on the first particle, it is completely locked, there's nothing liberated here. In the middle particle, 50% of mineral B is exposed to the outside, and 50% of mineral B is attached to mineral A. And funny enough, say it is here. 50% of mineral B is touching mineral A, and 50% of mineral B is exposed to the outside. So if you say, how liberated is mineral B, it's 50%. How floatable is this particle for a bubble? It's very floatable, because no matter where the bubble attaches, from a particle point of view, it's going to hit mineral B. So it's quite tricky, but if you keep track of grains and particles, then you can give a good context to what you mean by liberation. How would you write this down in terms of numbers? So what mineralogists do is they will make classes of liberation, and you can make as many classes as you want, whatever is practical in your case. Typically, if a particle has got less than 30% of the valuable mineral, or the grain that you're looking at, you would call that particle locked. If you're between 30 and 80%, very often people will say, well, that's a middlings. Half the particle is mineral, half the particle is gangue. Funny enough, the term liberated often applies to those minerals where they are between 80 and 100% of a particle. And then there's a last class called completely liberated, where it's 100% is the particle. But you can make as many classes as you want depending on the case that you have. And so it is also true for by surface. You can have many degrees of exposure depending on the case you're looking at. So here's an example that comes from an autosim scan, where they've got the states of liberation by volume in 10% increments. So you can see pentlandite is the light purple color, and in this class you have all the particles of pentlandite they could find. It was 100% liberated. The particles in this class are between 90 and 100% liberated, and so on all the way down. And as you come to the very unliberated material, you see all the other colors of all the other minerals that are associated with the pentlandite. Usually, this is presented in a graph, a cumulative graph, in these classes. 100, more than 90, more than 80, more than 70, more than 60, all the way through. What I want to talk about next is a thing called particle tracking analysis. It is really simply a more detailed form of the previous slide. In the previous slide, the results were classed into groups, 10%, 20%, 30% liberated. When we go to the particle tracking view, we say do not summarize any of the data. Keep all 100,000 particles that you've measured, keep the data of every single one, and have a look at that data set. This of course gives you a much more in-depth view of what the states of liberation are, rather than a summary view. So if you look at this slide, you will see it's a binary sample. It contains hematite, which is the valuable mineral, and quartz, which is the gangue. And just by looking at the picture, you can see the clean green particles are the hematite that's easily available to be recovered to product. If you look at the clean purple, pink particles, they are the clean gangue, easy to recover to gangue. But you can see in the sample that there are many, many particles that are locked in nature, that are going to form a middlings. And when you try and separate this by gravity, and you're getting a large middling stream, it's not the fault of the process, it's not the fault of the spiral, it's because the ore is not amenable to separating any better, because of this locked nature. In the bottom corner of the picture here, you can see the little scale bar. There's the 200 micron particle. So these are one size fraction that we're looking at. That's about 2 millimeters in size. The particles are about 2 millimeters big. But you can get this view for all size classes, right the way down to very, very fine particles. Of course, as you go finer, you may find that the amount of liberated particles increases. Okay, up to now, I've just shown binary particles, simple cases of liberation. The example I want to go through now is data from a real samples. This is a chromite sample where you can see that there are at least 11 identifiable minerals in the feed. Some of high density like chromite and magnetite, and many of low density like chlorite and talc and the pyroxenides. So to show the effect that liberation can have, let's assume two identical samples, sample A and sample B, and they are identical in many ways. They have the same size distribution, they have the same amount of mineral in every size class, they have the same head grade, they have the same grade in every size class. The only difference is the amount of liberation from chromite grains to gangue. So in sample A we'll have very poor liberation, and in sample B we'll have very good liberation. And you won't know this from chemical analysis, you won't know this from size distribution. You need the mineralogy to be able to make that distinction. On the top of the slide you can see the states of liberation. These are the cumulative liberation characteristics. The 100% liberated particles sit on this axis here. Each of these lines is a size class. So you can see the 1 millimeter material has 0 completely liberated chromite grains. As you go finer and finer, you're getting more and more completely liberated chromite grains. Compare that to sample B, where even at 1 millimeter, you've got 40% of the 1 millimeter chromite is liberated. So sample B is much more liberated than sample A. If you take the particle tracking analysis and you sort all 100,000 particles from highest grade to lowest grade in terms of chrome, you can draw the ideal grade recovery curves. This is the absolute best that you could do if your separation process was perfect. It shows that for sample A, if you want a high grade product, you can recover about 20% mass, and you'll get a 45% CR203 grade, and you'll get about a 50% recovery. That's the best you could possibly do. With exactly the same sample in terms of head grade and size distribution, just because liberation is better and you sort those particles, you will see that for this material you can get, say, a 35% yield to product at a 45 grade and at a very high recovery of about 90%. So this you can get on your feed material before testing whatever process it could be, whether it's a magnet or a spiral or a float plant. You can look at your feed mineralogically and give yourself the ultimate and ideal performance that you could expect. You could then do your actual test and see how close you are to the ideal. What's very useful about that is it says sometimes it's no use trying harder to do better. If you don't like the grade and recovery you've got, and you try harder and you try again, it may be wasting your time because it's not possible. Another place where looking at liberation and mineralogy is very good is after you've done your test and you have a product and you have a tails. And you can see that your concentrate hasn't made grade. Well, why not? And a simple SEM picture can show you a lot of information. So here we have a sample with 4 minerals: apatite, quartz, dolomite and feldspar. And there's a scale for 200 microns, so it's quite a fine sample. And this should be an apatite concentrate by these little tan grains. You can see there's very many of them. But it didn't make grade, and why not? And you can see the green particles of quartz are completely liberated and in the concentrate. So this concentrate didn't make grade, not because of mineralogical reasons, but because of a process inefficiency. There's no reason why the quartz should be there. They're not attached to any great degree to the apatite. It's a process problem. This is where you need to try harder. And simply also on the tails. This is in the tailings of that separation, where you want the material to be full of gangue, full of quartz and dolomite and feldspar. But you can see there is misplaced apatite here. Again, these apatite grains. This is slightly different. There are some liberated apatite grains in the tails, but many of the apatite grains are composite. They are tied in with quartz or dolomite, and there's maybe a reasonably good reason why they didn't make it to concentrate. Then not many of them are liberated. So these are just some examples to show how useful mineralogy can be and how useful understanding liberation can be when doing fines processing. So what are the main conclusions? Whatever process you're looking at, remember mineralogy. It doesn't have to be all the way down to the particle tracking analysis, but even under the optical microscope you can learn a lot. There are very many and very powerful mineralogical tools available nowadays to characterize fine ores. The definition of mineralogy is very important, and it can change depending on what you want to do. Are you looking at a leaching process, a surface-based process, or are you looking at a bulk-based process like gravity? A good understanding of your feed can give you an ideal target to work towards in your separation process. And you can then benchmark yourself. How well are you doing against the ideal? And then lastly, after you've done a separation, you can look at your product and tails and evaluate why you've done so well, or why there's an error and what you can do to improve it. Do you need to mill to liberate more, or is the process not as efficient as it needs to be? So one suggestion I can make is that during the life of mine, the ore characteristics could change over the years. It may be very useful to look and see, has the state of liberation changed? Have the mineral types changed? Have the mineral cleanlinesses changed? And that may be a reason why the process is not as efficient as it used to be. So it might be useful to look at your ore quality mineralogically, say once a year, to make sure that your plant is getting a decent feed. Thank you.